Hello and welcome from my side to the VDMA Shopfloor Data Session, OPC UA for metal forming. My name is Mark Glaser. I am working as a software developer for the Schule Group, and I'm one of the editors of the OPC UA for metal forming.
Yes, and my name is Götz Görisch. I'm the chairman for the Machine Tools Joint Working Group, where the Metal Forming Group is a subgroup of. And I will guide you through the talk today. And during that session, Mark will deep dive into the topics. We will start with an introduction into the domain, with the reasons for standardizations. Then we highlight the use cases and the harmonization which happens between the groups. And finally, Mark will dive into the information model and a few specifics about the information model, and will give you a live demo of how this looks in modeling tools and also in servers. And we will close that talk with a Q&A section in the end.
Okay, then I will go further and give you a short introduction how it all started. So what was the first step? We as a machine builder, we have the task to make the first step towards the VDW and the VDMA if we want to have a sector-specific companion specification. And we first make some thoughts about, and we define the task. So what was our task? We provide a standardized interface for digital solutions. That was one of the challenges. We have various digital solutions within our company nowadays in various kinds, and one of them are for cameras, and one of them are for monitoring some energy values. But all of them, they need some kind of standardized interface to communicate with signals. We had to choose between different protocols, and one of the pros of OPC UA is that it offers interoperability across the different control manufacturers. And that was one of the main pros that we take into concern, because we as machine builders do not focus only on one control manufacturer. We often have many control manufacturers which are combined within our machines. We also have a look at the state of the art. We have to choose between different companion specifications, and we make a little bit of an overview to see what are the signals that we already want to use in our specifications and what are the signals that are already defined. And we saw that, okay, in machinery and machine tool specification, we have a lot of signals that are already defined through the VDMA and VDW and the OPC UA Foundation. But we also face some challenges in the metal forming specific section. One of those challenges was, okay, we have very different tools in comparison, to example, to the CNC related production, because our tools, they normally exist out of an upper and a lower die, for example, or a matrix in between. And also, our machines sometimes contain more than one stage in one machine. That means that we have like 3 or 4 stages in one machine, and they all have different tools, and they are currently set it up at the same time. So this is like very specific, and that is not possible to mention with the machine tool specification. Another point that we consider through our brainstorming was, okay, we want to display and monitor those forming related process values, and we do need some additional parameters. We have so many working units that are closely related to the forming process, like, for example, a hydraulic unit, a cooling unit, a power unit, or the slide itself with the forming unit. And especially for the forming, we do have forming positions that are very specific to our sector, like we have the top dead center, bottom dead center, for example, and they are not defined currently in any kind of the specifications. So our solution, our goal was, okay, we have so much harmonization potential, but we need an industry sector specific extension. And this is how it all started. We do it not on our own as a Schule Group. We do have many participants who are joining us with the sub-working group. We started in April 2022 with the call for participation. We do have many different participants from many different sections, like the machine builders, automation systems, control manufacturers, as well as associations and the research institute. And we are spread like all over the world. We have a big community in Germany and in the northern of Europe, as well as in Switzerland, but also a big community in Japan who took part regularly at our sub-working group meetings. And we usually start our meetings with the one important mindset sentence that we always keep in mind, and I'd like to read it out. It is: the machine does not provide a structured and pre-processed overview of the current forming condition. It provides raw data signals which have to be standardized and communicated for the processing of the overall forming state. That was the one sentence that is always in mind when we try to define our signals and try to structure our different sections, and that's what it is all about. So for the next page, I will hand over to Götz.
Yes, thank you, Mark, for the introduction to that topic. As you heard, we found a lot of harmonization potential, and therefore the working group decided we want to make a sector-specific extension for metal forming machines, and they took the group. We took the machine tool specification and the machinery as the base for use cases we wanted to address. So these are the 10 use cases you have seen before if you attended the machine tool presentation in that series of webinars, but also most of them are similar to topics which are addressed by the machinery specification already. But then to come to the next point, as you heard from Mark, there are specific use cases for metal forming. So for sure, identifying the different manufacturers was a use case which is needed for a shop floor of different machines, but we inherited this from the machine tool specification. But access to repetitive and cyclic forming data and also monitoring what is happening in the tool, basically these use cases 2, 3, and 4 were crucial for the metal forming industry. Additionally, the specification makes use of the process value, which is defined as a building block in the machinery series, and extend that to specific requirements of the forming process, specifically the cyclic context, that in every cycle of a metal forming press or forging process, we get consistent data. And for sure, also specific use cases around what are the parts in the forming state, in the different stages of a tool Mark just told you. And last but not least, for sure, all the inherited use cases of the machinery and machine tool. If we come to the next slide, this picture is probably known to you, and you know how inheritance and reuse functions. Mark, can you click through? Yes, thank you. So basically we take type definitions from the base specification, which are inherited to machinery and machine tools, but also to taking certain things directly. In specific, what machine tool achieve here, I highly recommend you to review the presentation as soon as it is uploaded from the machine tools version. If we now come to where is the metal forming specification in this context, basically it inherits and uses types from the different specifications below. What is not shown here, how this build up of different namespaces and use of different namespaces is done. This we will see in the next slide. So basically we started using the base specification. For sure we used DI in industrial automation, and machinery. I told you that we are using the machinery process value, which inherits certain things from the OPC UA for PADIM, for process automation device information model, and as well as machine tools. All these namespaces and companion specifications build upon each other, and the metal forming takes and reuses the best what is needed in that regard. I hand over back to Mark, who will give you an overview of which processes in the machine metal forming industries we take into account.
Yeah, thank you, Götz. I will give you a short overview what kind of processes we want to address with that specification. So basically, the name of the specification is metal forming. We divide it into like 3 sections. We have the bulk forming, the sheet forming, and the powder forming. We already do a little bit of an extension of the traditional metal forming use cases like deep drawing or blanking, and inherit things like the powder forming, because the powder forming is just like a very interesting industry with which uses like the minimal material wastage principle, and which is on the forward steps in the future. With bulk forming, we address the process which refers to the use of raw materials and like processes, gears, bushings, and valves, as well as engine parts. And with the sheet forming, they are working basically upon sheets, plates, and strips. And I guess they are also one of the most known processes in the metal forming industry. Now I'm switching over to the task again, that we want to provide a standardized interface for all our formal metal forming related processes. Basically, the information flow is that we have our press machine, which is in the middle of the picture. On the left, we have our front of line, our in feed. On the right, our end of line or out feed. But basically, the press itself has a kind of a programmable logic controller with an OPC UA server that communicates with an OPC UA or on an MES server, for example, or which communicates directly with the cloud or the front end. Our PLC tries to manage the signals from different working units that are related. One of the most important is exactly the energy or the power unit. We need to have those energy to make the forming process come into the flow. Especially the forming unit with the cyclic context, as Götz already mentioned, and our use cases was one of the core points that we had a look at. And next to the forming and the power unit, we have a lot of other units that are needed to fulfill the forming process. For example, the cooling unit, the hydraulic unit, or even the lubrication unit. Those units basically measure process values like temperature, pressure, level, and so on. And the forming unit, we especially have the press force as a forming unit. And what I also want to mention is working with the tools that I've already mentioned in the introduction. What is very special at our use cases with the metal forming. On that picture below with the tools, we do have that case that I also mentioned in the introduction. We have a machine with like 4 stages and a 3x transfer. So that 4 stages are all inside one machine, and with each stroke or each cycle, or as we say in the specification, at each run, we put the part to the next stage with the transfer. So the flow direction normally from left to right, and then we have a ready formed part at the end of the right side of the image. So this is how it basically looks like in the real life. On the left side, we have our in feed with the blank coming in, or in that type, kind of material strip. We do have our machine. We cannot see so much because it is all behind that wall. But what we see is, okay, we have on the right side like kind of a table with some additional tools set up. That was also a thing that we tried to figure out with the specification. We do not only want to have the tools inside of the machine, also maybe the tools which are set it up for the next production steps. That was also kind of thing that we thought about. But basically, this is kind of a real life example where we try to implement our specification. Now I'm diving a little bit deeper into modeling and give you a few insights of what we achieved through that specification. As Götz already mentioned, a thing that is always in our mind when we were modeling the OPC UA for metal forming was that we need to have kind of a cyclic context. Because what is important for us as a machine builder for the metal forming is that we have the information of each process value, which is in context with each stroke or each run of the machine, to later on give information about the corresponding part that is produced through that run. We do have a high potential of harmonization that was already mentioned a few times today. I want to mention the process value type again, because that was kind of a very central type that we try to extend through that companion specification. The process value type itself contains the analog signal, for example, which gives information about the actual value, as well as low limits, high limits, an alarm suppression, 0-point adjustment, and so on. And have also some information about the set points, which marks, for example, like the static set points of the machine, as well as in status and general alarm suppression. This is basically good. We do also implement it in our specification. I will show you at the end of that presentation today. But it's not perfect if we want to have like a cyclic context, because it is difficult to make that context possible through every cycle if we have a very high frequency of strokes. And that was why we implemented that cyclic process value type, which contains a cyclic process value. And that cyclic process value has just 4 parameters. It has the actual signal, as well as the set point, and the very important cycle counter, which is just like a counter which counts every cycle and increases by 1 if the next cycle starts, and as well as if we're kind of a bit which measures if we currently have that cyclic process value measurement active. So that's basically all what we extended. We do also implement for that cyclic process value type another kind of object type, which needs to make the context between the cycle count and the current part ID. This is a thing that you can read in our OPC UA metal forming specification. You can reach it on the OPC Foundation site. And we do also make thoughts about is there kind of an alternative? And then we thought that it is also a good idea to implement an event-based mechanism for that cyclic context. And that's why we give also an alternative that contains an event that is containing the analog signal as a current process value. It implements a cycle count as kind of a counter, and a part ID, what is a string. And as some of the OPC UA servers already make use of those event types, of that customized event types, you can also change it and use those event types instead of that cyclic process value type. So you do have there also different possibilities. Next to the cyclic process value type, we also implement some forming conditions. and we call it the forming process condition class type. Within that forming process condition class type, we define some functionalities or some characteristics that can occur during a forming process. On the right side, you see the eccentric load exceeded condition class type, which I try to make a kind of a figure to give you some more information about what happens if the eccentric load exceeded. That eccentric load exceeded only happens if we have a press force, a total press force that is not centered on the middle of the slide. So this can occur if you have, for example, different force values on the inside or the outside of your tooling setup, because you have different actions which you want to perform, or the material has different properties on the inside as on the outside. So that's why you need a different adjustment of the force, and so it can occur that the force is not centered. But also there we have some limitations, because if the centered forces, the not centered force is too much on the left or the right side, we do have problems with our normal forming process. The horizontal of that slide is not balanced anymore, and therefore we can this can lead to a crash or some damage on the machine, and that's why we have there that condition class type which exceeds. Additionally, we have some other conditions like the overload triggered, as well as the process force, the general process force that's exceeded on the machine. Even there we have some limits, and all those were defined to prevent the machine from making a crash. So now I'm switching over to kind of a short live demonstration, because what was important for us was not only to show you how we define some things, it's also how to model that OPC UA metal forming specification, and that's why we switch over to a short live demonstration. First, I will show you how to model a namespace which includes the metal forming specification with the Siemens OPC UA modeling editor. Afterwards, I'll also show you a short introduction on how to implement it in, for example, a PLC. And then we also have a look at an OPC UA client, which then gets those signals that we defined during the process before. So I'm switching over to the OPC UA modeling editor. You see it now. The OPC UA modeling editor, first, before starting with modeling, we need to implement those namespaces. Götz told you a lot about those namespaces. We can't just implement it right here. We have the kind of an import possibility and can import all of those XML namespaces which we need to perform our metal forming specification. After we imported all of them, we need to make our instance namespace. I'm unlocking that namespace now, so we can dive deeper into the modeling itself. On the left side, you see the kind of the structure of the OPC UA structure with the machines folder. Within the machines folder, we have our basic machine. How did I do that? I just add an instance. I can call it, for example, the webinar machine. It's from the machine tool type. Right here. And then I can edit. I need to use my namespace. And then I have my webinar machine. Basically, that's how it's structured. I'm switching over to the Schuler machine because I also have implemented some more logics. Basically, what we do with the metal forming specification is an extension. So we use the machine tool and machinery specification and extended it with the things that we use to implement for metal forming machines. So the identification, I think it is well known for everyone who is interested in OPC UA specifications. as well as the monitoring is also known, equipment and components. Within the monitoring, there comes maybe one of the first interesting parts. We implemented with an element monitoring type our process working unit types. So if I maybe try to add one of those, I need to choose the namespace, then I can add an instance right here and dive deeper into working unit monitoring type. We have our process working unit type that we defined with the metal forming specification that is used, for example, for the cooling unit, the hydraulic unit, or so on. So these are units that are related to our forming process. But we also have the possibility to add, for example, the forming process working unit type. This is a working unit type that is the forming unit itself, because it inherits some additional information about, for example, the forming positions. I've done that right here. We have the forming process working unit type as the forming, the heating as a normal process working unit type, and there I want to dive a little bit deeper. Within those working units, we have different process values that we want to measure. I told you in the introduction that was one of the key points to monitor those different process values. Those process values, like temperature, they are not like stroke or run dependent. We measure them on a long run. That's why we use the normal process working unit type. And within the process working unit type, we have the possibility to add there the analog signal. We also have the possibility to add a few other components like the limit alarms, process value set point, 0-point adjustment. That was just what I said before. There's also so much harmonization from the process value group. Within the analog signal, we can also add the engineering units and the range. And that's what I want to show you, because that's interesting when we export that namespace model later on. We can already implement some values right here. So I say that this is defined in degrees Celsius, for examples. And we have also a range, minimum 200, maximum 800 degrees in that case, because it's about heating. And this is a thing that we can export to if we are working with that OPC UA modeling editor. So this is basically a process working unit type. I told you that we also use a forming process working unit type, and within that forming process working unit type, it's similar to the process working unit type, but it has the addition of that forming positions. And within that forming positions, we can choose between the bottom dead center, the retract position, the start position, the top dead center, and the touch position. They are all defined in our specification that is uploaded, I told you before. And those forming positions, they remark the position of the slide at the corresponding stroke. So as you can hear, they are corresponded to a stroke, and therefore we need a cyclic process value. Okay, that's to the part of the forming. As you can see, we also have implemented a thing like an machinery item state, which gives us an information about each of the units. That's also possible for the heating, for example. I can add a kind of a machinery item state to get some information of that heating unit. So it's very modular. Another point that is important right here is equipment. Give you a quick overview of the equipment, what have changed in comparison to the machine tool type. That is basically inside of the location. We added there the information about the orientation, about the stage, and about the position. Orientation is, for example, if you have a bending machine, you can place the tool with the orientation front or back. The position means the absolute position in millimeters from the centered point of the machine to the left or the right side. And the stage is what I've shown you before with the tool, with the like 4 stages. It is possible that our machine has like 4 stages or even more. And that's what the stage parameter identifies. That is a kind of a normal forming tool type. We also extended the multi-tool type as a multi-forming tool type, and it's nothing more and nothing less than an extension with that forming tool type right here. So we do have more than one forming tool type in that multi-forming tool type, because it is also possible to like build up one tool setup with multiple forming tools. With those numbers, I just want to identify that we have an upper and a lower tool, for example. I can also give them more clear names, but it's just like a basic example for us. And right here in the components, you already know it from other specifications, we can give some additional information, some static information to those external components that we use within our specification. For example, here, the heating unit. If I'm ready, then I can export it. What is important right now is that I include the values. That was what I adjusted before, because I added some information about the heating with the engineering units and the range. And to export that information, I need to include the values. So I already did it, and I can show you how I implemented it in our PLC. This is TIA Portal PLC from Siemens, which has the possibility to add the server interfaces with the OPC UA communication. Right here, you can just implement those XML file that we exported right before with the Xiome, and you can map the signals from your data blocks directly to the specification right here in the TIA Portal. And that is maybe all of the magic right here. What you need to have a look at is at special OPC UA data types like localized tags. There is a special kind of encoding structure with those Siemens PLC, as they use, for example, a struct with an encoding mask, and now the OPC UA server inside of the TIA Portal knows how to handle it. So as you can see, that PLC already runs, so I can also have a look at the OPC UA client. And I've connected the machine with that OPC UA server, and then got, for example, there's information about the identification. So we do have there some real-world values. Also, I have a look at the heating. That was the thing that I've shown you before. We do have the information about the heating temperature. And then we defined like the range. That was the thing that I've adjusted in the Xiome directly and imported with the include values. And right here you can see that it just takes those values that I've imported, 200 and 800, and also the engineering units, that is in degrees Celsius. You can see it right here. We can also have a look, for example, at the identification. What is nothing more than static information. Where's our heater from? And yeah, basically, that's all what I want you to show with that live demonstration, just to give you an overview of the process flow, starting with modeling, with the implementation of further defined namespaces, which build up the base for our developments with metal forming, then creating an instance model, go deeper into modeling those instances, and then export it, mapping it with the PLC itself, and deploy it so we can see those signals right here with the OPC UA client. Okay, then I'm switching back to our presentation. Just give you then an overview at the end what those kind of sample instantiation would look like in a more formal way. with our metal forming extension. The most of the work that we did was in the monitoring area and the equipment area. As you saw before in the monitoring area, we adapted the monitoring elements with the process working unit type. Right here, for example, we have a cooling unit on the left side, which has different types of process value types, like the main line and return line, and also gives feedback what the current state is with the machinery item state. We do also make achievements with the forming process working unit type, which is closely related to our forming unit. It inherits like the forming positions and different cyclic process value types, like the force on different positions, maybe the infeed, the outfeed, and the total press force, as well as, for example, the stroke or slide adjustments. And last but not least, with the equipment, we do implement a forming tool type, which is an extension of the base tool type, especially in the location, and also the same for the multi-tool type, which is nothing more than an extension right here with the forming multi-tool type. Now, what is the current state of the art? We did it in that sample instantiation for one machine. That OPC UA for metal forming part 1 was basically also for to just give the overview for one machine. But if we have a closer look at the press line, for example, it is nothing more than a concatenation of like 5, 6, or 7 single press machines. And it is also possible to instantiate like 5, 6, or 7 of the single press sample instantiations to have a total overview of the whole press line. In addition, it's also possible to make like one of a main instantiation that contains all of the most important signals from each of the press machines. That's maybe also a thing that we need to talk about in the future. If we are ready to make further investigations in the OPC UA metal forming specifications with another part, to have a closer look at it, what is maybe needed if we talk about press line and the whole system, and not only kind of a single press. Okay, now switching over back to Götz for the last sentence.
Thank you, Mark, for that deep dive into that specification. As you heard, we are working closely with the harmonization effort. Here as an outlook, currently in the machinery, we are looking into that overall structuring of machines, of lines, of cells. That is definitely on our table. The overview of companion specifications, you know that slide already. I highlighted here OPC UA 40503 for metal forming. That is the specification you want to look into if you have further questions. But if you want to reach out to one of us, if you come to a question next week, please feel free. Mark, can you go to the last slide? Please feel free to drop us a line. If you want to get involved in any adaptation, or if you see use cases which should be addressed, please feel free to reach out to us to put it on the table of the working group. That's all from our side. Thank you, Mark, for the presentation. And back to you, Mark, for the Q&A session.